Let's learn about Hertzsprung-Russell diagram. We call this as HR diagram. So this HR diagram is a graphical tool that astronomers use to classify stars according to their luminosity, spectral type, color, temperature, and the evolutionary stage. So we're going to learn about this in step by step, and basically this is the periodic table like in chemistry, and this is the periodic table for stars. So we call these as HR diagrams or Hertzsprung-Russell diagrams. So this is a close picture of the diagram. So as you see here, in this y-axis or the vertical axis represent the luminosity. So all the way top, you should be able to see more luminous stars, and down here is more dim stars, so low intense stars. So luminosity is represented on the vertical axis, and the luminosity increases when you go high in the vertical axis. Then on the horizontal axis, we can see the surface temperature in degrees. So the cooler or a cold stars will go all the way to the right of the diagram, and the hot stars will be towards left. So this axis or the horizontal axis represents the surface temperature, where the temperature increases towards left. Now, in the HR diagram, we should be able to see a main sequence in the middle, represented by this region here. And then we see giants and the supergiants over here, red supergiants and the blue supergiants. And all the way down here, we see white dwarfs. And the sun that we see in our sky is located in this region. That's a main sequence star. Then the HR diagrams depicts, as I mentioned, the temperature, color, spectral type, luminosity, and the radius. So let's pick 4 stars. One star labeled as A, somewhere in this region, star B, star C, and star D. So which star is the hottest one? Can you figure it out? So try to read the spectrum here. So hot means in this region. So if you see some star that's somewhere here, because this side is the hottest side of the diagram, so star A should be the hottest, right? So answer is A, and it is a white dwarf star. So white dwarfs combine relatively low luminosity with high surface temperature. Here, the low luminosity, because it's like kind of below in the vertical axis, but in towards all the way to the left in the horizontal axis. So this is a white dwarf which has a low luminosity with high surface temperature. So since the temperature is high, each square foot of surface emits a large amount of energy. So a relatively small surface area is required to make the star's luminosity as low it is. So these stars are typically a size of Earth. It is small, but high surface temperature, low luminosity, so it makes the stars relatively small in size. So it is about the size of the Earth. All right, so which one is the most luminous star? So the luminosity increases in the vertical axis. So among B and C, one of these stars should be the most luminous one, and C is all the way top, right? So the answer is C. The star C is high luminous than the other 3 stars. So these are red giants, and also it can be a red supergiant combining high luminosity with relatively low surface temperature. On this side, the left side of the diagram is represent low surface temperature stars. No, it's high temperature, right? It's high temperature. stars, and no, I'm right. So this side is the low temperature stars. Yes, let me go back and see what it's read, right? So here on this side is low temperature, this side is high temperature. So here the star C, um, it's a red giant which has a high luminosity with relatively low surface temperature. So since the surface temperature is relatively low, each square foot of surface emits relatively light energy. So a huge surface area is required to make the star as luminous as it is. These stars might be as large as or even larger than Earth orbit. So they are really large stars. So Betelgeuse is one of the red supergiants. Which star has the largest radius? That's a good question. So which stars are big, right? So here my answer will be C. So as you notice, those stars have high luminosity but low surface temperature. So in order to have a high luminosity, even though it has a low surface temperature, the area of the surface should be bigger. So star C does have a high surface area. All right, so among these, which star is a main sequence star? So this middle area is the main sequence. So star D should be a main sequence star. So let's learn about the significance of the main sequence. So main sequence stars are fusing hydrogen into helium in their cores like the sun. Then the luminous main sequence stars are hot and blue. Less luminous ones are cooler, yellow, or red. So these are yellow and red ones. These are the hot blue ones. So in the main sequence, you may find a whole variation of luminosity. And the high masses of stars go all the way to the top here, like in blue stars, and the low mass stars stay somewhere here with the low surface temperature. Sun is somewhere here in the middle. So the mass of a normal hydrogen burning star determines its luminosity and the spectral. So if you think about the life cycle of our sun, so it started from in this region, like birth of the sun, then now it is somewhere here, 4.5 billion years approximately, and it will be gradually warming up, end up being a red giant after about 10 billion years. Then it will become a planetary nebula, and then it's turned to be a white dwarf. So that is the approximation. So after 14 billion years later, our sun will be a white dwarf. Let's learn about life cycle of stars in the next class.